Hi, I'm Schantz with Q-Track Corporation in Huntsville, Alabama. This is an extended version of my talk on energy flow in standing waves, originally presented Thursday, September 25th at the 2014 Antenna Applications Symposium at Robert Allerton Park in Monticello, Illinois. I'll begin with some historical background and talk about energy flow in a variety of canonical standing waves. I'll talk about the applications of this perspective on electromagnetics, as well as some of the fascinating implications of this energy flow in standing waves perspective. First, I'll take a look at some historical background from Newton to Schelkunoff's discovery of impedance. Now, Isaac Newton discovered and put forth his law of universal gravitation in 1686, and for centuries thereafter, aspiring scientists tried to cast their theories in a similar Newtonian mold. So when the pioneers of electrical science began making some of the first quantitative measurements of electricity and magnetism, they tried to emulate Newton's law. Good case in point is Coulomb's law for the force between charges. The prevailing electromagnetic perspective was that charges and currents interacted with each other through the intervening space without any intermediary, an action at a distance theory of physical behavior. That orthodoxy was challenged by Michael Faraday, who came up with the idea of lines of force pervading the spaces between charges and currents. Faraday's fields became the foundation of our modern theory of electromagnetics, reduced to mathematical form by James Clerk Maxwell. Now, contemporaneous with Maxwell, William Thomson, or Lord Kelvin, discovered that we can assume there is an energy, a local energy associated with electric and magnetic fields that is proportional to the intensity squared of the field at a particular point. And that was a cornerstone principle of Maxwell's theory of electricity and magnetism. Well, not long thereafter, Poynting and Heaviside, more or less simultaneously, came up with the theory describing how electromagnetic energy flows in Maxwell's theory. They discovered that if you take the cross product of the electric and magnetic fields, it gives you a vector dubbed the Poynting vector in honor of its discoverer that describes the local power flux or power per area associated with electromagnetic energy transfer. Now, until that time, people thought of circuits in kind of a plumbing analogy, that current flows through a pipe conveying energy to a resistor, which is a bit like a turbine, and then a battery is something like a pump pumping that electrical fluid through the circuit. The point of view of Heaviside and Poynting was a little counterintuitive. That point of view suggested that the energy is carried by fields around the vicinity of the wire, from the battery on one side to the resistor on the other. And of course, you can understand why the theory was controversial for a while. You can calculate the power much more easily by simply multiplying voltage and current. It's much more difficult to integrate the Poynting vector over the normal of the cylindrical resistor surface. So the reason, though, that we use this more complicated Poynting Heaviside theory is ultimately it does a better job of describing how reality works, and it led to a better understanding of such phenomenon as the skin effect and AC resistance, as well as the electron drift velocity. The signals are propagated through the fields at the speed of light, but the charge itself moves at a much slower rate through a circuit. Now, Oliver Heaviside was a truly remarkable individual, a self-taught electrical engineer. He not only rewrote Maxwell's equations in their present-day form, another of his achievements is he came up with the idea of energy velocity. He proposed that energy moves with a velocity equal to the ratio of the Poynting vector to the local energy density. Now, he only derived this in the context of plane waves, however. William Sutard's Franklin took a look at what happens when waves interfere with each other in free space. And he identified two special cases: a pure wave, where the field impedance is the same as the impedance of free space. So in other words, the normalized impedance, lowercase z, is plus or minus 1. And the energy velocity, here normalized to the speed of light, is equal to 1. Energy travels at the speed of light in the case of a pure wave. When you have an impure wave, that's when you have a superposition or interference of multiple waves propagating in different directions. The balance of electric and magnetic energy, which are equal for the case of a pure wave, becomes disrupted. The local impedance is no longer necessarily equal to the free space impedance, and as we'll see, the energy velocity is less than 1. Now, the first individual to explicitly identify that energy velocity could be less than 1 appears to have been Harry Bateman in 1915. And more recently, Gerald Kaiser pointed out that the energy velocity may be treated as a local time-dependent characteristic of electromagnetic fields. Sergei Schelkunoff is the individual to whom we owe the concept of field impedance. The identification of the ratio of electric to magnetic fields as the impedance Z is well known, but in his original Bell System Technical Journal article from 1938, he pointed out a number of other interesting features that are relevant to the present discussion. First, he pointed out that we can regard impedance not only as an attribute of the medium, but also as an attribute of the field. He noted that we can apply the one-dimensional transmission line concept to understand energy flow in higher dimensional problems, neglecting the dimensions that are not necessarily relevant. And he applied that 1D transmission line model concept to great effect in understanding antennas, particularly biconical antennas. And in that context, he noted you could assign a direction to the impedance. A forward propagating energy might have associated with it a positive impedance, and reverse propagating energy would have a negative impedance. We'll be using those ideas in the present context. Now finally, let's bring these two ideas together, energy velocity and impedance. We can define a normalized impedance relative to the 377 ohm impedance of free space. And the normalized energy velocity with respect to the speed of light turns out to be a relatively simple quantity that's actually quite reminiscent of the transmission coefficient that we have in conventional microwave theory. So that's a bit of historical background. Let's take a look at a variety of canonical standing waves. First, the simplest possible case, let's imagine a little infinitesimal wave colliding head-on with a little, E cross H giving rise to a pointing vector propagating in opposite directions. Now, if we have a case of constructive interference, the electric fields combine constructively and we end up with twice the electric field. But of course, we understand that the energy is proportional to the field squared. So this suggests that we have 4 times the electric energy. Similarly, in the case of a destructive interference, it looks as though the unit electric fields with unit energy combine destructively to cancel out. So how do we resolve this apparent puzzle? Well, if you pay careful attention to how the magnetic fields are behaving, you'll note that when we have a constructive interference of electric fields in this head-on interaction case, we have a destructive interference of the magnetic field, and vice versa. The destructive interference of the electric field gives rise to a constructive interference of the magnetic field. So we do indeed have 4 times the energy associated with that electric field on superposition, but it's because all of the magnetic energy is gone. The magnetic field is 0. The magnetic energy has all transformed into electric energy. The characteristic balance, an equal balance of electric and magnetic energy in a pure electromagnetic wave has been disrupted and swings all the way to the side of being purely electric. Similarly, in the destructive interference case, all of the electric energy is gone because it's transformed into magnetic energy. So what we have here, and what's interesting to note, is in each case, one or the other of the fields is equal to 0. So the Poynting vector is equal to 0. So in other words, in free space, when we have these elemental electromagnetic waves interfering, we have the Poynting vector equal to 0, at least momentarily. That means no power is flowing. The energy is momentarily static. So electromagnetic waves interfering with each other in free space can give rise to instantaneous static concentrations of electric energy or magnetic energy. We can understand a little better what's going on by appealing to image theory. In image theory, if we have a source of electromagnetic energy radiating in the presence of a ground plane, we can solve for the fields by assuming that we have an inverted virtual source symmetrically positioned on the other side of the ground wave. We add up the fields from that inverted source and cancel out the electric field tangent to the ground plane. That satisfies the boundary condition on the ground plane, so by adding up the two sets of fields, we end up with a solution for the fields on the left-hand side of the ground plane. Well, now consider what would happen if instead of a virtual source, we put a real inverted source on the other side of the ground plane. I think we'd all agree that the energy from the left-hand source bounces off the ground plane on its side, and the energy from the right-hand source bounces off the ground plane on its side, the plane on which that tangential electric field is equal to 0. But now, what happens if we remove the plane? The boundary condition is the same, tangential electric field equals 0. The math is the same. The theoretical description, according to Maxwell's equations, are exactly the same whether the ground plane is there or whether we remove it. And I argue in both cases, the electromagnetic energy is bouncing off of that surface on which the tangential electric field is going to 0. Now let's see what happens when we look at some simple waves interacting on a 1D transmission line. So let's just take a look at a Gaussian doublet wave combining destructively, so that the two waves propagating in opposite directions exactly cancel out at z equals 0 on this transmission line, precisely at time t equals 0. And figures are in my paper, so I will cut to the chase here and show a space-time diagram for the total energy. In this space-time diagram, the horizontal coordinate, or the z coordinate, is the length along that 1D transmission line, and the vertical axis describes the time. What you see happening is the two waves come together, and initially they combine constructively. The first lobe has an electrostatic node combining constructively. Then as the two waves overlap, we end up completely canceling out the electric field, and we have two nodes of magnetostatic energy. As the waves begin to separate, we end up with a single node of electrostatic energy, and then the waves move on past. So the fields, or the waves themselves, propagate through each other. But in so doing, they end up exchanging their energy. No energy flows through that point where z is equal to 0. And there are a number of other interesting features. You'll notice the energy in the leading, or in the trailing edge of the forward propagating wave becomes the energy in the leading edge of the reverse propagating wave. Similarly, the energy in the trailing edge of the reverse propagating wave becomes the energy in the leading edge of the forward propagating wave. So no energy transfers through z equals 0. The waves effectively trade their energy. And finally, the energy retains the same order in space. You'll notice that the streamlines of the energy don't cross. They retain the same order under the interaction. Now, let's take a look at what happens when we have an arbitrary impulse. What you'll see happening is when two arbitrary waves interact in this one-dimensional context, and I've given a couple examples of waves of different shapes, or little wavelets of different shapes and amplitudes. Effectively, what happens is the energy in the smaller wave accretes to the leading edge of the larger wave. And then as the two waves move through the zone of the interaction, the larger wave ends up spinning off or spitting out enough energy to reconstitute the smaller wave as the two waves separate. So in effect, electromagnetic waves on a 1D transmission line behave a lot like an electromagnetic Newton's cradle. You know, in a Newton's cradle, the pendulum wave action starts on one side of the Newton's cradle. You drop a couple balls, it propagates through the cradle, and the same number of balls move off on the other side. The wave motion propagates through the cradle, but on the other side, it's a different set of balls, and the balls retain the same order in that wave interaction with the Newton's cradle. Electromagnetic energy on a 1D transmission line behaves the same way. The waves propagate through each other, but the energy of which they are comprised or which is associated with them is exchanged from wave to wave. So really the fundamental rule of understanding how energy flow streamlines work is don't cross the streams. Now let's take a look at harmonic standing waves, and this is basically having two waves interfere with each other of different amplitudes or magnitudes but the same frequency. We can take the local time-dependent energy velocity and integrate it weighted with respect to the local energy density. Here I've done a space-time integral to average it, and what you find is the average energy velocity can be related back to conventional microwave parameters like the reflection coefficient and the voltage standing wave ratio, or VSWR. Let's take a look at a couple of, or a number of interesting cases. We'll start with a voltage standing wave ratio that's infinite. This is the case where you have equal forward and reverse propagating waves. In that case, the average energy velocity is 0. But the energy flow itself is characterized by the energy bouncing back and forth between local electric and magnetostatic nodes. This is a case that was examined in detail by Jerry Kaiser. As one wave starts to dominate, one wave is the forward wave in this case is a little larger than the reverse wave, a net energy flow begins to emerge. When the VSWR is 5.83 to 1, the average energy velocity becomes 1/3 the speed of light. And you can see if you pick a particular energy flow streamline, to go 1 unit of distance takes about 3 units of time, at least on average. As the forward wave gets larger with respect to the reverse wave, we have a voltage standing wave ratio of 3 to 1. The average energy velocity here is 0.6, 3/5 the speed of light. So in order to go 3 units of distance, it takes 5 units of time. What you see happening is the dominant energy flow is moving to the right or in the forward direction, and then periodically the weaker reverse energy flow induces a slip in the energy from lobe to the leading lobe to a trailing lobe. When the voltage standing wave ratio is 2 to 1, the average energy velocity is 0.8 or 4/5. So to go 4 units of distance in z takes 5 units of time. Here you can see that there's just an occasional slip associated with that much weaker reverse propagating wave. So those are some examples of how energy flow works in a variety of standing waves. Now I want to talk about the applications of this point of view of electromagnetics. The one of most personal and professional interest to me is in geolocation. Q-Track works with using near-field signals to provide precise location information. And in one of our studies, we took a look at how AM broadcast signals propagate through an urban area. We took about a square mile area of Huntsville, Alabama that you see there on the left, and the little blue dots denote where we sampled the electric and magnetic fields. We took the ratio to calculate the impedances, and we discovered something that was a little bit surprising. Even though we were in what should be the far field, many wavelengths from the transmit tower, we saw that the impedance varied significantly from the ideal free space value. This surface plot is normalized, so 0 dB corresponds to 377 ohms, and then it's plotted in a dB scale. So yellow means the impedance is 20 dB, or about a factor of 100 low. The dark red would be about a factor of 100 high. So the yellow areas show where there are large concentrations of magnetostatic energy in this far field broadcast signal. And the red areas show where there's concentrations of electrostatic energy. Originally, we thought this might be some form of near-field scattering off of the local clutter, the buildings and so forth. But it happens over such a large scale that we believe the correct interpretation is that we're looking at the waves actually interfering with themselves, a direct and, say, a reflected ray off of a nearby mountain. Another application is in antenna systems that will be robust in the presence of multipath. If the multipath consists of waves propagating in opposite directions, what you'll find is, although you may have a fade or a null in one field, it's not necessarily going to be a fade or a null in the other. In this one-dimensional case, consider an electric antenna located at z equals 1. It would not pick up any electric field. But at that same location, z equals 1, the magnetic field is at its maximum. So in principle, you could have an electrically small antenna array with an electric and a magnetic sensing antenna, and have an antenna system that would be more robust with respect to multipath. And finally, this concept helps in the understanding of how small antennas work. Last year at the Allerton conference, I presented two different theoretical derivations for why the gain of an electrically small antenna should be equal to the loaded Q times kr cubed, where r is the radius of the boundary sphere of the antenna. We can apply Schelkunoff's idea of treating the fields as a one-dimensional transmission line, and by plotting his expressions for the electric and magnetic dipole impedance on a Smith chart normalized to the free space impedance of 377 ohms, you get this nifty yin-yang pattern of the impedance. Now this is a variation on a Smith chart introduced by Philip Carter, more or less at the same time Philip Smith came up with his original chart. The Carter version of the Smith chart shows the lines of constant phase angle. Those are the arcs that you see on the Smith chart. Now, that phase angle of the impedance is effectively the phase difference between the electric and magnetic fields. And just as in AC electronics, where we can take the phase difference between the voltage and the current and derive a power factor, we can similarly take the phase difference between the electric and magnetic fields and define a power factor. That tells us the ratio of the real power to the apparent or total power flowing through back and forth at a particular location. So ultimately this ends up providing a third derivation for that small antenna gain formula. This is a sneak preview of a full paper that I'll be presenting at the Loughborough Antenna Conference in November. So those are a few of the interesting implications or applications of looking at electromagnetic energy flow in standing waves. Now I want to conclude by examining some of the interesting implications of this perspective. When we analyze an electromagnetic problem, the principle of superposition lets us disregard almost everything that's going on in the environment. We can focus just on the particular narrow frequency that we're interested in analyzing. So for instance, if we want to understand how a cell phone might transmit a signal to a receive tower, we could model a direct optical ray and, say, a ground bounce reflected ray. We add up those two contributions and we get our answer and we move on. But of course, there's a lot more that we're ignoring that's taking place in the environment. If we look at all of the various optical rays, we have a complicated network of crisscrossing optical rays in the vicinity of our cell phone and tower. And we understand by how electromagnetic energy interacts with each other that we have electromagnetic rays or electromagnetic energy streamlines do not cross. They bounce off of each other in a manner more like the figure that you see here. So the energy itself meanders in a complicated path. A particular optical ray is actually comprised of different energy at different points of the optical ray. And of course, this is a gross oversimplification because the actual bouncing and interactions take place on a distance scale on the order of about a half wavelength, which is much too small to show on a diagram of this figure. But even if we were to describe it on that half wavelength scale, we're ignoring all of the other electromagnetic fields that coexist with that particular frequency we're studying in the propagation environment. In particular, during daylight hours, we have a solar flux of a kilowatt per square meter illuminating our environment. Once the ground comes into thermal equilibrium with that solar flux, we have an equal and opposite infrared thermal flux, a factor of 15 lower in frequency and longer in wavelength. And the space-time energy flow diagram shows roughly how that energy flow would look between those waves, the 15-to-1 difference in wavelength on a one-dimensional basis. And of course, there's every other radio signal in the environment, everything from millimeter waves down to Schumann resonances. So the implications are really counterintuitive and rather surprising. First, it's unlikely that any of the transmitted energy from the cell phone actually ends up at the receiver. If you think about it, the energy coming out of the battery of the cell phone and radiated into space, the cell phone signal is the faintest whisper compared to the cacophony of other signals in the environment. That little whisper of energy immediately gets swept away by the much larger, more dominant energy flow in the local environment. As the signals from the cell phone propagate through the intervening space, they gently perturb or nudge the energy flow one way or the other. And finally, as they reach the vicinity of the cell phone tower, they act so as to knock a little bit of that local energy flow, disrupt it, and get it to be accepted into the receive antenna at the cell phone tower. So the average energy velocity is actually going to be less than the speed of light. About the only case where the energy velocity will approach the speed of light is when you have one dominant energy flow. Say you're studying the flow of sunlight through the inner solar system, or in an anechoic chamber with a very high power signal whose total power is higher than the total noise floor integrated across all frequencies. So it's pretty rare that that's going to happen in practical cases. So in general, the average energy velocity in most practical electromagnetic problems in reality is less than the speed of light. The startling conclusion is that reality is mostly comprised of near fields and standing waves, not of far fields. There is a vast collective superposition of electromagnetic waves all around us that we're interacting with all the time, but that we can ignore for most practical problems. So in summary, impedance has a dual nature. As Schelkunoff observed, it is a property of media and it's a property of fields. And those two perspectives on impedance don't always necessarily provide the same answer for what the value of impedance is. In particular, impedance discontinuities, whether of media or of fields, can reflect energy. The energy velocity can be related to microwave parameters, and the surprising conclusion of all this is that electromagnetic energy is largely decoupled from the fields themselves. At any given moment and at any given location in space, there is an energy proportional to the square of the field intensity. But from moment to moment, it's not necessarily the same energy. The electromagnetic waves that propagate through an environment don't behave as optical rays. Rather, the energy meanders or drifts or is perturbed under the influence of the collective superposition of fields in a particular environment. And as a consequence, the typical electromagnetic energy velocity is less than the speed of light. I'd like to thank you for your interest in my presentation, and if you do have any questions, you can feel free to address them to me by my email address, h.schantz@qtrack.com. Thanks for your interest and attention.